are going to present you another lesson that belongs to grade 12 chemistry. So you all are welcome to the lesson here that we are going to present you regarding the very first unit. Students, we are going to talk about the quantum theory including electromagnetic radiations. So it's the lesson about quantum theory and electromagnetic radiations. So you might wonder whether we have any such there in our very first unit. Yes, you have. It's under the very first competency level 1. Students, in the competency level 1 we talk about that it says uses electronic arrangements and energy transactions in determining the nature of matter. Under that, we are having the competency level, it's 1.2. Student, it says there, investigates the different types of electromagnetic radiations. So, it's here in this, we are going to look at what electromagnetic radiations are. And then after we are going to talk about what the quantum theory, what are the points that we are having there in quantum theory. Students, the content, the lesson content, subject content, when you check for that, you could find that out, the wave particle dual nature of matter and electromagnetic radiations. We are going to find out few terms having speed, wavelength, frequency, energy. So we are going to find out, we are going to talk about these equations as well. So it's C equals nu lambda. It is nu. Nu stands for frequency. So, and it's E equals h nu. Again, we are going to call it the Max Planck's energy equation. And we are going to find out this equation as well. We are going to derive that. Students, lambda equals h divided by mc. mc stands for the momentum. So, then it's electromagnetic spectrum also we would be having under this lesson. Students, let's find it out what electromagnetic radiations are. Students, do you know what electromagnetic radiations are? Electromagnetic radiations. Radiation is, it means that when you have any energy mode, energy type propagating or kind of dispersing, spreading all around without having any support of a medium. That's what we call a radiation. Then students, when you check for electromagnetic, this is a mode of energy. That's what we are talking here about. Students, in this, when you have this energy been traveling without having any support of a medium, then we call them electromagnetic radiation. So, these energy modes are having electric fields, magnetic fields, those are oscillating electric and magnetic fields perpendicular to their traveling direction and perpendicular to each other. That's what we denote by electromagnetic radiation. Students, then when we check for these electromagnetic radiations, you could find it's been a mode of energy for the very first time. And students, it does not need any support of a medium to get travel. Then it consists of waves with oscillating electric and magnetic fields which are perpendicular to the traveling direction as well as perpendicular to each other. Then students, further, these all electromagnetic radiations have one unique property, is their speed, is their, let's call, velocity. They all have the same velocity. It's exactly 2.998 into 10 to the power 8 meters per second. Or let's round it to 3 into 10 to the power 8 meters per second. Then students, these electromagnetic radiations, a mode of energy that get transport in the form of a wave. Therefore, if you denote this direction here as the propagation direction, it's you could find that out there, they are having a magnetic field oscillating. What is oscillating? Its magnetic field strength is increasing, decreasing and changing the phase. So, here it's decreasing, 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 then after it's in the other phase increasing, increasing. What's that? Increasing, decreasing. It's the magnetic field strength. So, then it's further getting decrease, decrease, decrease and it goes other side. So, then it again increases, increases, increases. That's what we call oscillation. So, it's oscillating magnetic field you have. In which direction? If this is the traveling direction, students, it's in the direction which is perpendicular in 90-degree angle, perpendicular to traveling direction. You have oscillating magnetic field there. Then further, there is an electric field as well. So, that also would be oscillating, means changing its field strength. So, it would be perpendicular to both. Both means perpendicular to traveling direction in one hand, as well as it's perpendicular to magnetic field that you have got oscillating magnetic field earlier. This is perpendicular to that magnetic field as well. That's what we say or denote as an electromagnetic wave, electromagnetic radiation. It's a radiation for the reason does not need any aid, any support of a medium. Okay, then students, it's the same. So, those when you check for an example, light energy. The light energy that we know very well, it's an energy mode. So, students, believe it, it also is an electromagnetic radiation, a mode of electromagnetic radiation. So, then they all have this common velocity. It's the 2.998 into 10 to the power 8. So, it's the 3 into 10 to the power 8 meters per second. But we have got used to say that it's the speed of light. Students, it's just for the reason light also is one type of electromagnetic radiation. So, in that aspect only you could talk about light in that manner. It's actually, it's unfair saying it's the speed of light. It's better saying it's the speed of all the electromagnetic radiation. Therefore, light also belongs to the same category. So, electromagnetic radiation. Therefore, it's the speed of light as well. Okay. Then students, it's to the propagation direction. It is the propagation direction. It is a perpendicle you have, another perpendicle you have. So, those are the two fields, two oscillating fields. So, students, it's electromagnetic radiation. What's the difference between this and this? Before giving you that difference, let me explain you regarding a wave, a sigmoidal wave. Students, this is what we use the shape as to explain what's a wave. So, regarding this, when you take this section of this shape, it is one wave. Students, so here in this you have another wave. So, then what is the length? This is the length. What is the length of a wave? Length of a wave is nothing else but wavelength. Right? So, then students, it's the wavelength, length of a wave. How would you measure that? Could you use a ruler as to bring here? It is not physically you could find this kind of wave. So, could you use a ruler to measure the length of a wave? No, you can't. Students, it's in that aspect, you could do something like this. So, this is the maximum height. We call it the crest. So, you get two adjacent crests. Then you find the distance between two adjacent crests, or let's call it them peak as well. So, then it's the length of, it gives you the length of the wave, the wavelength. We denote it by the letter lambda. So it's the lambda, it's the wavelength. The other property regarding waves is the frequency. Frequency stands for the number of waves that produced within a unit time. Or it stands for, in another sense, it stands for number of waves passed by. Means when you consider one certain point, the number of waves passed by within a unit time is referred as the frequency of that particular wave or particular energy mode. So therefore, those are two properties that very important to denote, to give the properties, give the shape, give the nature of a wave. So regarding a wave. Then students, these electromagnetic radiations also are types of waves. Therefore, this is the wavelength. So here this is the wavelength. Now you could see the difference between those two wavelengths. The down wavelength is quite lesser, smaller than of above one. So then when you check for the number of waves, it is within this length, the number of waves you could find here being more than here. So then students, it's with increase of wavelength you could find decreasing the number of waves, means the frequency, number of waves produced or passed by within a unit time. Then in the other hand, other sense, it's with decrease of number of waves confined within a narrowed range, confined within a given range. It's the wavelength could be found being increased. Okay, so the wavelength and the frequencies are two important characteristics that we need to know regarding those electromagnetic radiations. Then students, we have found out that for electromagnetic radiations you have a frequency as well as a wavelength. But all the electromagnetic radiations are having one specific, one certain speed or velocity we could call it. It's 3 into 10 to the power 8 meters per second. Then if it is one certain or fixed value standing for all the electromagnetic radiation, then students, how could we find it out, this fact that there are different types of those electromagnetic radiations. It's getting change in their wavelength, or if the wavelength is different, frequency would follow the wavelength, so would be different. But maintaining those frequency into wavelength product as a constant. Let me reveal you this fact. Students, when you talk about the length of one wave, it's the wavelength, lambda. And when you talk about number of waves formed or passed by within a unit time, then when you multiply these two together, you would get the distance travelled by one wave within a unit time. In other sense, it's the speed. Okay, it's the velocity in a certain direction. Students, therefore, it's this lambda into nu gives us the speed or velocity of that particular electromagnetic radiation. So all the electromagnetic radiations are having the same speed or same velocity. For that reason, it's different electromagnetic radiations would have their wavelengths being vary, as well as the frequency. Then students, in that manner having different wavelengths as well as frequencies, you could find it out different electromagnetic radiations categories being possible. So it's radio waves, microwaves, infrared, visible light, ultraviolet, X-rays and gamma rays are few such categories of electromagnetic radiations. Hope you could understand what are these electromagnetic radiations and how are they varying one to another in the aspect of wavelength and as well as frequency. Okay students, it's what we have already discussed are there, you could now find it out. So students, it's you have those two terms, wavelength and frequency. It's the distance between two adjacent peaks or between two adjacent troughs. Troughs are the bottoms of those peaks that you could find out there earlier. So stands for wavelength. Then students, it's frequency stands for the number of complete wavelengths or cycles that pass a given point at each second. So students, it's then let's find them out. The speed or the velocity of those all the electromagnetic radiations would be the same. It's 3 into 10 to the power 8. So let's find it out how we could have those different questions asking either to find out the wavelength or in the other hand to find out the frequency given the other one. Means when it is the wavelength to be found out, you would be provided with the frequency. When it is the frequency to be found out, you would be provided with what? Wavelength. So this is an example question standing for that. Students, it's given that the yellow light given off by sodium vapor lamp used for public lighting has a wavelength of 589 nanometers. Calculate the frequency of this radiation. How could we find that out? Students, it's we know this equation, C equals nu lambda. So C is the speed, it's 3 into 10 to the power 8 meters per second. Then in that we have got this is the what? It's the lambda. Lambda is wavelength. So it's they are asking us to find it out the frequency in the question. So it's what's the wavelength? Students, it's 589 nanometers. When you talk about nanometers, you can't substitute wavelength in nanometers here in this equation for the reason it's given here in the units of meters per second. So students, you need to transform those nanometers into meters. How could you transform nanometers into meters? You could reach that when you multiply that 1 nanometer into 10 to the power minus 9. It would be 1 meter. It would be equal to 1 meter. So therefore, let's multiply this 589 by 1 into 10 to the power minus 9 to transform that into meters. Then students, it's nu. Nu is the frequency. Frequency could be found out as 3 into 10 to the power 8 ms minus 1 meters per second divided by 589 into 10 to the power minus 9 meters. Meters to meters, those would get cancelled off. So you could find it out the answer. How would you divide 3 by 589? In that, I need the support of a log table. So let me show you how to use a log table to get this. Okay, students, the division of 3 by 589 could be easily done with this. With this means a log table. So let me show you how we could use a log table on this purpose to find out the answer of this. So you need to find out the log of the top value. It is, we write it as 8 point. You need to use the log table as to find it out. The value of 3 means you need to read it as 3.00. So it's then 0th of 30 you need to refer. You need to find there out. Then students, it's 0th of 30 is 4771. Okay. Then secondly, it's you need to refer the down value, denominator. So then it's 589 into 10 to the power minus 9. Then when it is 10 to the power minus 9 and it is with 589, right? So you need to first write this in the scientific way as 5.89 into 10 to the power minus 7. Then you bring that here as it's minus 7. So therefore bar 7 point, then 9th of 58. It's, I have it here in the log table. 9th of 58 is given at, there, say 7774. 77774. Then it's the division. So in log it's the subtraction. So 11 minus 4 is 7. So it's 6 minus 7 is 9. It is again 6 minus 7 is 9. It is now, it remains 3. So 3 minus 7 is what? 3 minus 7 is 6. Then students, it's 7 minus 7 minus minus 7. Minus into minus is plus. So therefore it's 7 plus 7. So it's 14, right? It's 14. Okay. Then you need to write the antilog of that. When you write antilog, that value before the decimal point, you need to raise to the 10th power, saying it's the 10 to the power plus 14. Then students, you find the antilog of this. It's 6997. So 6997 is there. You could find it 6990 there at the 0th of 50. So 6998 is there, but it's 6998. So let's use that there. So it is 50 and 1. Students, is the way you could get the answer. So the unit is per second. Okay students, that's how we could use this table called log table, found revealed by John Napier, to use in such sums. Okay, then let's continue our lesson. Okay, it's the same sum. You could find it here being addressed, being found the answer in this way. Okay, as we have seen already, it's different electromagnetic radiations are having different wavelengths as well as different frequencies. Then students, it's for that reason, when you manage as to get all the possible electromagnetic radiations, and when you keep them in the ascending order or descending order of their either wavelength or frequency, you would get an array. You would get a continuous spectrum, is what we call electromagnetic spectrum. Those earlier mentioned electromagnetic radiations, here you have in a belt. Students, it's, I could name them as gamma, X, UV. So it's visible, infrared, microwave and radio frequencies, radio waves. Then it's in the way that we have given here. It's in the way that in the increasing order of their lambdas, of their wavelengths, it has been given. So in the other hand, it's in this direction, we could call it's the increasing direction of their frequencies. If it is the increasing direction of wavelength, it's the same, the decreasing direction of frequency. So then they are inversely proportional to each other. What? The frequency to its wavelength. Then students, it's, you have here white light. White light being differentiated into its component colors. It was first being done by Sir Isaac Newton, passing this white light through a prism. So it was a glass prism he used. So passing that white light there, he differentiated those into basically 7 colors. Here what you are having are those. We call them the continuous spectrum of white light. Okay, in that manner, we could have an electromagnetic spectrum within a given range. If you mention all the frequencies, if you place all the frequencies that it belongs there, it's the electromagnetic spectrum. Okay. Students, here we are having an example question asking what's the wavelength in nanometers of the light radiation with the frequency having 7.35 into 10 to the power 14. Okay. So, it's the same equation we could use here as well. It's C equals nu lambda. Students, at this time they are providing us the nu. It's 7.35 into 10 to the power 14. It's with the units per second. You remember, always substitute those values with the units. Then, hope you know this already. Students, it's 3 into 10 to the power 8 meters per second. So, what we need to find here out is the lambda. Lambda is the wavelength. Students, wavelength, but in nanometers they ask. Let's transform that our answer into nanometers finally. First, let's find the answer. Okay, let me use the log table again. Okay, here let's find it out. Lambda equals 3 into 10 to the power 8 divided by 7.35 into 10 to the power 40. So, in log, you need to first find the log of 3 into 10 to the power 8. So, is 8.4771. Then students, the other value, its log could be found out as it's 14. 14 point, it's you need to find out the fifth of 73. 73 fifth. It's, I got that, it's 8663. 8663 here. Then what we need to do is subtract. Division in log is the subtraction. Students, when we subtract that, it's 3 by 1 you can't, but 11 you could. So, it's 8. Now, it's 6 you have there. 6 minus 6 is 0. It's 1 here and it is 14 minus 8 is 6. Now, it's not 8 anymore, it's 7. Now, you have 7 minus 14 is minus 7. We call it bar 7. Okay. This is the log value. You need to transform that into, means you need to find antilog of that into real number. Okay. Then students, it's 10 to the power minus 7. You need to find it out. The antilog of 6108. What's the 6108? It's antilog. I could find it out. 6107 I have here. It's the 8th of 40. Students, it's 8th of 40. Then it lacks 8th of 40. There I have 07. So it lacks 1. So another 1 here it requires. Then it's in the units of meters. Then you need to transform in the question what they have asked for. It's in nanometers. You need to transform these meters into nanometers. How could you do that? Just multiply that by 10 to the power 9. Okay, it's billion. Okay, then students, when you do that, it's 4.081 into 10 to the power minus 7 into 10 to the power 9. Now it's in nanometers, Nm. Okay, the answer is 408.1 nanometers. See how easy, when you use the log table, you could easily get the answer. Okay. Then students, here you could find it, it's the same. You need to know always the velocity of all the electromagnetic radiations is the same, is 3 into 10 to the power 8 meters per second. Then when you are provided with the wavelength, you could find it out the frequency. The other way, when they are providing you the frequency, you could find it out the wavelength as well. Okay. Then our next topic is about the quantum theory. So students, let's find it out what are we having there in quantum theory. Okay. The scientist named Max Planck in 1900 century, he presented this idea for the very first time. What's the idea? The energy, when the energy is absorbed by those cold matter, or when energy is released by those hot matter, as in the form as of electromagnetic radiations, it would be done this energy as quantized. Quantized means discrete amounts in energy. That was his idea. It was not like continuously or continuous amount of energy. Those energy either be absorbed or released. Done. It would not be in the form of continuous amounts of energy. It would be in the form of discrete amounts of energy, be absorbed or released. So that's what his point was. So energy is quantized. Quantized means in unit amounts you could find them out as a gathering of such units. It's discrete amount wise you could find them out, especially when it happens like an absorption of energy by those cold matter or release of energy by those hot matter. Okay, so that fixed energy amount could be named as quanta. Then students, he further said when it is electromagnetic radiation, all the electromagnetic radiations are having their own frequencies. Okay, so he said that these frequencies would be standing for the energy amount. In other words, it's the energy amount of each quanta, each energy packet, discrete amount would be directly proportional to its frequency was his idea. He presented this idea as the energy amount of that small unit. So, is having a frequency, that energy amount would be directly proportional to that frequency, that particular frequency. So, then after you could find a constant for proportionality. We call that, to honor him, it's the Planck's constant, for the reason that it was first revealed by Max Planck. Students, its energy of that such small amount would be equal h nu. H means the Planck constant, it takes the value, here you have 6.626 into 10 to the power minus 34 joule seconds. Then this is the frequency. Frequency into Planck constant gives you that small energy amount. Okay, so then the same idea was further developed by Albert Einstein. Students, it happened in 1905. So Albert Einstein, he observing this Max Planck's quantum theory that energy either emits or absorbed as discrete amount, he further told that energy is having a smallest unit or smallest amount. It's like matter is having of atoms. So these energies are quantized, amounts are having their own smallest amount of energy. So this smallest amount he denoted with the term photon. Photon was the name standing for that smallest amount. He further said that when you talk about the matter, matter is having its own smallest unit. Similarly, it's similar to matter. Here in energy also you have a smallest unit as well. So it's the photon. Photon could be named as the particle of energy. Particle of energy is the photon. Okay. So then he further told that its energy of a photon equals Planck constant into its frequency. It's the same equation revealed by Max Planck. But now with another advanced meaning, he gave the same idea but saying now energy is having its own smallest particle, energy particle. It's a photon. Okay, it's an example question being given as consider the electromagnetic radiation with the wavelength 400 nanometers. It asks to calculate the energy of one photon. Okay students, we could easily do that using that equation. E equals h nu. But here they have not given you the nu is the frequency. What they have given you is just the lambda. Lambda is the wavelength. So then we could use this. It's C equals nu lambda. Then you find nu equals C divided by lambda. Then substitute it there. Then the same equation, we could pronounce it in this way as well. It's hc divided by lambda equals to that E. E is the energy amount standing for one photon there. Okay, then students, let's find it out. The energy amount standing for one photon of the electromagnetic radiation having the wavelength 400 nanometers. So, Planck constant is the same, 6.626 into 10 to the power minus 34 joule second. Then, hope you know this, the velocity of electromagnetic radiations, it's 3 into 10 to the power 8 meters per second. Then students, let's divide that by lambda is 400 nanometers in meters is into 10 to the power minus 9. So, it's in meters. So, we need to find it out the answer standing for this sum. Okay, let me use the log table as to show you how to get the answer standing for that. I'm now ready with a log table as to solve this. So, students, it's bar 34. So, you need to find the second of 66. 66 second is there, 8202. Then, it's small sixth column. So, it's having 4. So, 8206. 8206 I have there. So, then it's 8 point. You need to find out log of 3. It is 4771. Let's add them together. It's 7, 7, 9. It's 12 here. So, then when it comes to this, it's plus 1 you need to add there. Then it's plus 9 with bar 34. It's bar 25 it's going to be. Okay. Then students, I could sort this out as it's 4 into 10 to the power minus 7. I'll take it as bar 7 there. Then students, when you check for the log, it's 6021. You get there. You need to subtract that, isn't it? So, you need to subtract 1 by 7, it's 6 there, it's 5, it's 9, then 12 minus 6, you can't subtract 6 by 2, that's 4, therefore, you need to take 1 from that. So, when you take 1 from that side, when you don't have 1, you need to complete that, you need to fill that giving bar 1 there. So, then it's bar 1 with this bar 25, it becomes bar 26. Anyway, 12 minus 6 is 6. Then bar 26, it's minus 26 minus 7. It's plus 7. Minus 26 plus 7 is giving you bar 20, not 20, it's bar 19. So, you could find it out the antilog value. Antilog value of that gives you the energy of one photon there. Okay. So, let's find out the antilog. It's 10 to the power minus 19 anyway in joules. So, 6956, the antilog of that you could find there as 6955 you have, it's 49th, 6th, then you lack 1, it's in the first column you find 1. This is the answer standing for the energy of one photon. Then students, when we go back to the question, it further says calculate the energy of 1 mole. So, 1 mole of photon, 1 mole means you have that Avogadro number. So, that number of photons, not protons, photons you need to find out here. This stands for 1 photon. So, then after for the part 2, when you find out the energy, now let's denote it by E dash, the energy standing for that number of photons, it's the same value 4.961 into 10 to the power minus 19 joules. Simply you multiply that by 6.022 into 10 to the power 23. Then that's the energy. It stands for 1 mole of photons. Then students, we already know the log value of this. it's this, bar 19.6956. So let's find out the log value of this. It is 23 point. It's the second of 60. You need to go to the second of 60. You have 7796 with, then to the second of 60 you need to add small second. It's having 1, 7797. So I'll write it here, 7797. Here you need to add these all together. It's 13. So it once comes here, it's 15. So it's another one comes here, it's 17. It's another one comes here, it's 14. So one comes there, so making it bar 18. So bar 18 plus 23. It's when you add them together, it's plus 5 what you get there. Then students, the answer would be the antilog of this. So you could finally find it out as 10 to the power 5, it's in joules anyway. So it's the antilog of 4753. Let's find it out where you have 4753. 4753 could be found out there. It's at the 8th of 29. 8th of 29 is carrying 4742. So it lacks another 9. So you need to go for 6th column. So it's there, you could find the answer. Okay. Finally, we have found the answer standing for 1 mole of photon in joules, as it is 2.986 into 10 to the power 5. So you could transform this into kilojoules. So it's then students 298.6 kilojoules. So I could show you the same here, as it's 299.3. So there would be, when you use the calculator and log table, there could be a slight difference that you would reaching. So anyway, is how we could find it out, the answer standing for 1 mole of photon there. Okay, let's go to the next point. Okay students, it was Louis de Broglie extended the idea that if radiant energy could under appropriate conditions behave as though it were a stream of particles, means photons, or matter under appropriate conditions, possibly would show the properties of waves. So with that idea, Louis de Broglie showed that those smallest energy amount, if it could exist or if it could represent particles behavior, then a particle could behave as a wave. Well, means it's wave particle duality. His idea, his thought was there. So students, it was Albert Einstein. He proposed that the smallest energy amount of that any electromagnetic radiation, naming it as a photon, that photon's energy, he presented that in an equation like this. So stating that photon's mass is, if it is m, then if you give the velocity as c, you could find its energy being E equals mc squared. Then students, Max Planck presented this equation, that the smallest energy amount of any such electromagnetic radiation would be directly proportional to its frequency. Therefore, it was h nu, the frequency into Planck's constant, that smallest energy amount. So combining these two together, it was Louis de Broglie finally derived this equation. Let me show you that the way he did that. So it was E equals h nu. So for the reason nu equals c divided, c is the velocity, divided by lambda. So he then brought forward this. So it was hc divided by lambda equals that smallest energy amount. Then it was photon's energy equals mc squared. So according to Albert Einstein, combining those two together, it's one of this c would get cancelled with one of them. So then he finally derived this equation as to find out the wavelength. The wavelength standing for that smallest energy amount. That smallest energy amount means the energy amount of that one photon, or the smallest energy amount that you find within electromagnetic radiation. So it is we call de Broglie's wavelength. Louis de Broglie derived this equation as to find, as you could then find out the wavelength of that. Then it did not stop there. Students, it went ahead. Means he tried to apply that in all the other objects moving in a speed. So then he thought, okay, if energy is having particle behavior, those particles would be having energy behavior, means wave property too. So that's what we call wave particle duality. At the same time, a moving object would be having wave properties also. According to this equation, it suggests something like that. Then students, in an example it could be shown as, so when you talk about an object with the mass 1 milligram, so you could find out its wavelength, substituting those values to the equation. So you would finally end up with this. So then think about an object with this mass, means 1 milligram. It's a small mass, but it also is having this much of very, very small value standing for its wavelength. Then students, it's at the very beginning when we start thinking of those matters which are moving fast, means moving with a velocity, they would have wave character too. So then we had that idea, isn't it? So but at the very beginning when we start applying that into that equation, so on such matters we end up with this kind of wave property, wave behavior. Its wavelength was very, very small. It is not a realistic wavelength. Therefore students, we can't state that all those big matters when they are moving fast exhibiting wave character. So then when we try to apply that concept that moving matters with a speed are carrying wave behavior, so we could then suggest some wavelengths on those. So we could apply these values. It's an electron with this mass moving in this speed or velocity, let's say. So a golf ball and a bullet at the next time and a motor car, so moving in these different speeds. When we try to apply these values in that equation, the equation is lambda equals h divided by mc, the velocity into mass. So then students, you would end it up with these answers standing for its wavelength values. Look at these magnitudes. So these are not actually realistic values. Those values, though we get just values standing for their wavelengths, they are not truly, actually we can't call them waves. They are not truly waves. Okay. Then students, when we consider such a small particle like an electron, it's okay treating them as wave for the reason it's having quite realistic wavelength. So this de Broglie's wavelength equation reveals the fact that when very small particles are moving in such speeds, they are exhibiting wave behavior as well. That's what we call wave particle duality. Okay. Then students, with this, we could extend the idea that electrons when you have around atoms, students, around the nucleus when they are revolving, was questioned the Rutherford model with the idea that they would lose energy and finally spot on the nucleus. But with this concept, electrons exhibit wave, particle, both behaviors at the same time. Then an electron is not just a matter only, not just a mass only, but an electron could exhibit energy properties, energy behaviors as well. With that idea, we don't want to make it spot on the nucleus, because an electron itself is a mode of energy. If it's an energy, what's the point of spotting that on the nucleus? So then it was Niels Bohr got this idea and presented his model at the next time. So this is the beginning. This is the idea that Niels Bohr started with presenting his model regarding the atom. Then students, it reveals a new path for us. Actually, it was for Niels Bohr, it revealed a new path. So then electron exhibits wave as well as particle behavior at the same time. Then it's no need to talk about losing of energy and spotting of the electron at the nucleus within an atom, when you find an electron revolving inside the atom. So we are going to find it out as in our next lesson, as the next model standing for the atom. So students, we are going to meet you there talking about the Bohr's atomic model. We have come to the end of the lesson. So we are going to wound up here in this lesson. So it's a gentle reminder that you could watch these lessons again and again when you visit YouTube channel NIE. So you could discuss the matters that you find within this lesson with your school teacher, so as to resolve them out. Okay, with the hope as to meet you in our next lesson, we are going to say you goodbye.